a few more minutes for other partners to join, so we'll start around 11:05,
Okay, no
if you
issue.
kindly agree. So, sir, can we start?
Yeah, please go ahead.
Okay. So, a very good morning, good evening, or good afternoon, depending on wherever you are joining us today. Today, we are extremely privileged and honored to have Professor Jyotsna Kumar Mandal, sir, amongst us. My name is Devoshi Basu, currently the chair of IIT Student Branch, IIT Kharagpur. And I, on behalf of the entire team of IEEE Student Branch IIT Kharagpur, would like to welcome Professor Jyotsna Kumar Mandal, sir, amongst us. And we are extremely grateful to you, sir, for accepting our invitation and kindly give us your valuable time and share and agree to share the knowledge with us. So today, sir will be talking on the reversible transform computation-based image authentication. Though sir is extremely popular with for his activities and research work, and does not need any separate introduction, but still, for our audience, I'd like to introduce sir briefly. So Dr. Jyotsna Kumar Mandal MTech in Computer Science from University of Calcutta in 1987 and awarded PhD in Engineering in Computer Science and Engineering by Jadavpur University in 2000. Working as a professor of Computer Science and Engineering at University of Kalyani currently, he is a former Dean and Faculty of Engineering and Technology and Management of Kalyani University for two consecutive terms during 2008 to 2012. He is also a former director of IQAC and chairman CIRM Kalyani University. He has served as a professor of computer applications at Kalyani Government Engineering College for 2 years. He has awarded 28 PhD degrees, 2 submitted and 6 are pursuing, supervised 3 MPhil students, more than 80 Master MTech students, and more than 130 MCA dissertations. He is a guest editor of MSc Journal as the Extra Index of Stranger and published more than 450 research articles, out of which 190 articles in international journals. Published 12 books from Springer, LP, Germany, IGI Global, etc. He served as secretary in IIT Kolkata Center and chairman of CSI Kolkata chapter and CSI Siliguri chapter. So this is a very brief introduction about sir, and talking about a very quick summary of the topic on which I will be talking in detail, and obviously he's an expert in this field. So, like in this talk, the fragile watermarking techniques have been proposed for gray or color image authentication based on Discrete Hartley Transform, uh, Legendre Transform, Binomial Transform, Stirling Transform, and group of linear transformations for dihedral group of order 4. Now, two processes corresponding to each transform has been discussed for 2 cross 2 and 1 cross 2 sublines. In addition, the quality enhancement and genetic algorithm-based optimization have also been elaborated to enlighten the post-embedding quality improvement over the watermarking technique. The basics of steganographic approaches are also discussed at the beginning. So, with this, I'd like to hand over the podium to Sir, and a few more information from our participants who are joining across various parts of the world, that we are also live streaming our event in our official YouTube channel. So you can also join there as well. And please keep your mic and camera off during the talk, and put your questions in the chat box. And obviously, take the most opportunity to interact with our guest speaker to gather the most of the knowledge that you can. And this is all. And with this, I'd like to hand over the podium to sir. And like not to forget that we are also privileged to see Dr. Devoshi sir amongst us. So like we are expecting sir sometime in both of you, sometimes in our campus physically, but thanks to this online mode that we are having both of you together amongst us. So without not wasting much of time, so let's hear from sir this great area of expertise. Thank you.
Thank you, Devorsi. Good morning, everybody. I am honored. And regarding Kharagpur, so my birthplace is at Midnapur, and secondly, my wife's place at Midnapur town. And I oftenly go to Vidyasagar University, and this is uh, one of my own birthplace. So uh, I have some emotion towards this. So thank you for inviting me for this, and love to go IIT anytime, any
Sure. Thank you.
situations. Thank you very much
You
for
can, sir,
inviting me.
please share your screen and
Yeah,
let's start.
let me share my screen.
Yeah, it's visible, sir.
Yeah, it will come. Uh, so it's visible now,
Yes, sir. It's visible and
and
fine.
I'm also audible.
Yes, sir. You're also audible.
Okay. So thank you very much. So today I am going to give some glimpse of uh, authentication, basically image authentication based on transform computation, which is reversible transform computations. And my talk will be restricted with the embedding and dealing with real component of the transform coefficients. So in this lecture, I did not consider the embedding in the imaginary component, though we have some works, some of our scholars working on the imaginary component, but towards the end, I will give some glimpse of that also, a light on that, how we can achieve that type of things, because how do you embed in an imaginary component complex conjugate in that way. So basically, my objective of this talk is just to deal with the security in communications and transform domain computation and reversibility, image authentication, authentication using steganographic application, and their work related this objective, some enhanced methodologies, because when I am going to embed some information, secret information, so what in terms of image, I am injecting some noise. So how do we optimize the noise, and then towards the end some analysis of results, and how do upgrade and how do enhance the results. So we know that the communication is an integral part of our day life, and most of the people, including rural India, has a handheld device which is capable of communicating. And all of the transmission are hopping based transmission. That means it's not from end to end that I am transmitting, it will go directly to the receiver. So in between you have a mesh networks, and that's why there is a possibility of perturbing the information uh, purposely by the intruder or by some malicious nodes or agent. So that is why we are imparting security in transmission. So today we shall basically discuss the authentication part. So if we think of the aspects of security, so there are two aspects. One is your cryptographic aspect and another one is your steganographic aspects. So in cryptographic aspects, what we are doing, we are scrambling the source ensemble or input ensemble, that means plain text, and we are associating with some keys when we are scrambling, and then so this is then the complete ensemble, encrypted ensemble is communicated through the open channel, and then it is being received, and the key is sent maybe through private channels, or there may be some key exchange policies, and then the data is retrieved back, which is called the decoded. So this is called the cryptography. So but the problem of this cryptographic system is that, you see, I cannot ensure the non-repudiation. That means if in the middle someone changed the information, I cannot ensure that is it the same information communicated from the source where I am intending the information from that source. So that one question is there. So to overcome this problem, we have another methodology which is called the steganography, or I may say it is invisible communication. So I think all of you know that the lizards on the leaves of the tree can change the color of his skin to the color of the leaf or the stem of the tree. So Here also the same thing. Unlike the cryptographic system, we are here injecting some information or injecting some noise in terms of secret code. It is my secret code, but in terms of the image, it is a noise. But I am keeping the visible property of the cover near equal to the original, cannot be exactly same. That is the field of steganography. You see the two aspects. One is cryptography, another is steganography. So these two aspects are quite just opposite in directions. Because if we think of the parametric test, if we go for chi-square test, we are going for the homogeneity test in your cryptography, but heterogeneity in the cryptography. But if we think of the steganography, it is a homogeneous. That means the minimum change, how we can keep the change minimum and inject the information or secret code into my cover. So here you see we have a leaf. Some petals are there, and you see that I have inserted the steganographic writing here. So this writing of your steganography here, I have inserted here to some extent. So it may be visible. I can identify here that okay, it may be steganography. So if I ask the questions that can you identify this leaf? So you will say that yes, I know three petals are here, I can identify this leaf. So now I have cropped the leaf, and you see I have shifted this more here, you see, towards this. So now if I ask the same questions, can you identify this leaf? You may say maybe. Now again I am cropping the leaf, and you see that I have inserted much more part. So now it may be geography, it may be steganography, it may be cryptography. Now if I ask the same questions, that now can you may say no. But in terms of technology, your technology says that yes, I can identify this leaf through embedded information into the image, and that is the field of steganography. And we are going to deal with this image authentication today. So whenever we are talking about any cryptographic things or steganographic things, so there may be intruder who can intrude our systems, and that's why we have incorporated various keys to overcome these problems. Maybe symmetric key, maybe asymmetric key. What we are doing, either we are sharing the key in case of symmetric key cryptographic system, or in case of asymmetric we used to exchange the key. So this is to be dealt sensitively during this process, whatever may be. Normally we use a private channel for sending the authentication codes or other. So basically we have two paradigms. One is your encryption, other one is your authentication. So my domain is cryptography, watermarking, steganography, and particularly in steganography we are going for spatial domain and frequency domain. What is the applications? Authentication of image, authentication of legal documents, authentication of various documents. So this is the formal definitions. I am not going into that. Whatever I have given in the slide, it's okay. So what we are doing, we are going for a data hiding, we are going for secret image transmission, ownership verifications, copyright protections. These are various applications of the steganography. You see, some histories are there. So the history of steganography, it was earlier called the steganographia. You see, in 15th century, it's a German about named the Pythamas. On the face of it, the three books are about the magic, but they are contain the encryptic treatise. That is the history says. Now here interesting information that an ancient Greek named Hystereus was fomenting revolt against king of Persia and needs to send the message. What he did? Save the hair, put the tattoo, then along with the tattoo, the secret information is written here. So after 1 month or so, the hair grows. Now can you see the tattoo? Can you see the code? No. But it is there. So then he boldly go from that kingdom to other kingdom and says, you save my hairs, hair is saved, and the secret information is recorded. So this is another example of ancient steganographia. You see, the third example is this, is that you see that in 5th century BC, so someone wrote a warning message between this wooden plaque. So they've written the message, mail the wax, put the wax into the plaque and bolt it, and draw some painting and gift it to them. So there they thought that it is something different, devolted it, mail the wax, read the message. So these are called visibly invisible communications. Only the intended participants or the intended people can identify this. Now this is another interesting example. You see that this is a sweater. So I am wearing the sweater. I am loitering in the mall and everywhere. So no one will notice that. So if it is a winter season, so no one will think that why the girl has wear a sweater. But the intended recipient, he will see what? That he will see that this may be some code written. What is the code? You see, this may be the Morse code written on the chest here. So some Morse codes are written. That means I'm reading the information, and the girl is loitering in the place, but no one other than the intended recipient can understand, because the intention is not there. Code is visible to all, but only the intended recipient will see and act accordingly. So in World War 1942, so teeny dots were made on the watch. Watch were handed over to the wire field. They used to blast the dot and read the latest strategy of the wire. And this is, you see, one posture detection. That when the thing is that, so we cannot torture the prisoner. It is the UN system. But you see, from the face, we can see that they are tortured. So that means from here we can go for it. Now let us see one application of this steganography. Then we shall go into the technical details. You see, this is one legal document. What inside the legal document? You see, we have some stamps and we have some written statement and we have some signature stamps. So a lot of things are there jumbled together. But if we think of the same thing into some of electronic form, so how we have to write in your MS Word, so that can be changed very easily. So how do you authenticate that? You see, it can be changed. You see how the change? You see, the positive has been changed to negative, the maximum has been changed to minimum, and the strong has been changed to weak. So how do you authenticate that? So here, let's see one process. You see that this is a change document. So you generate the message digest. What is the message digest? That means you are generating a fixed size code, suppose 128-bit or 160-bit, from any size input message, and you embed it as a steganographic manner into the stamp paper. So it is visibly invisible. So now you put the code to a place just like your PKI infrastructure, and you send this who is intended for it or when it is required. So at the receiving end, what you will do to authenticate, if it is required to authenticate, you generate the MD5 and you extract the digest. So if this part is changed, then this MD5 will be different than this. So if it matches, now authentication of the document is satisfied. So these are some of the applications generated, that this gold coin is embedded on this Lena image. That means you see the visibility of both images are almost original. And during the authentications, you extract the gold coin. What is the gold coin? It is a two-dimensional matrix. And you compare for authentication. Now, whatever I have told you, the physical.
Sir, here how we can deploying the Legendre transform, sir, in this context.
You see that we shall transform the image. I'm coming to that. I'm coming.
Okay, sir. Carry on.
Coming. Wait, you'll get it. You'll get your answer. Definitely. I'm just coming. How do you accomplish that? So here also, you see that I'm embedding the signature into this cover image for authentication, and I am extracting it for authentication. But what is the problem? That there may be degradation of the cover image. So you have to go for some image enhancement algorithm to enhance the cover image. But my intention is to authenticate. So I can accomplish the task in spatial domain as well as in the spectral domain. So let us consider the technicality now. Okay, these are the theoretical perspectives and the visibility. So what is an image? The image is a two-dimensional matrix, nothing else. So you see, this is a two-dimensional matrix, and this is a unsigned. This is an unsigned integer, 0 to 255. If it is a color image, R, G, and B all 0 to 255. So only unsigned integer if you define when you are processing the image and these pixels, then it is good. Otherwise, the storage will be doubled. So now, how do we accomplish the steganography on this? Let's go for it. Let us consider the LSB steganography first, just to highlight. So I am first considering the general considerations in the pixel domain or the spatial domain. So let us take 9 pixels from this Lena image. This part, I have taken 9 pixels. Okay, I have converted to binary. So all pixels will be 8-bit because this is unsigned integer, 0 to 255. So it is 8-bit. So in steganographic applications, the fascinating thing is that all of the handle, whatever you are doing, it is only 8-bit unsigned integer. So now I have a secret message here, 365. What is the message? Is 1011011101. Okay, and I am inserting onto this LSB only. Okay, all LSB. Just I'm taking. There are 9 pixel and 9-bit here. So all LSB. Suppose I'm embedding. Now, why the steganography is so successful and degradation is less? I'm just going to give you that example. So you see, this is my cover image, and you see I have embedded this one to here, this 0 to here, like this. You see this 0 to here, this one to here, and this one to here. Now, how many changes I have incorporated by doing this? You see, if I have a 1 here, and if I am embedding a 1 here, it is a no change. 1 to 1, 0 to 0, it is no change. If it is a 0 to 1 and 1 to 0, then it will be a change. So my probability of change is maximum 50%. So that is the thing that I can consider, that we have successfully hidden 9 bits and only 4 bits are changed. So this is one major aspect. And secondly, you see that we never see the single pixel when I am taking the image. We used to see the perspective or neighboring pixel of the image. And when I am going for an LSB steganography or LSB insertion, what is the change? It is plus minus 1 only. If I use this bit, it will be plus minus 2. If I part up this bit, it is plus minus 4. Plus minus 4 means if it is 0 and if it is 1, it is plus 4. If it is 1, if it is 0 embedded, then it is minus 4. So this is another major aspect, that which this is your MSB and this is your LSB. So that's why we used to embed towards LSB. We used to embed towards the least significant bits. So still now we are perturbing up to 4th or 5th bit. But the thing is that when I am embedding a 1
Sir,
here,
are these four changes are creating hiding the whole word 365, or we have to create much more
yeah,
changes?
definitely, because these are there. You see that I have embedded 1 here. It was 1, but it is 1. But I will consider that this is my embedded bit. What was there, I will not consider. I will consider only what I have embedded. You see, the same thing is here. You can see that this 1, 0, 1, 1, 0, 1, 1, 0, 1. So you see, the same bit is here. So if I extract from the LSB, I will get this information only, the 365. Is it understood?
Yes,
Okay.
sir. Yes, sir.
Yeah. That means 0 is there. I am embedding a 0. That does not mean that I am not inserting my bit. I am inserting. But what was there, I am forgetting. What I have inserted, that is my concern. I have to extract it. And secondly, you see, during what is that? It is degrading the image. Either the pixel value is increasing or the pixel value is decreasing, whatever may be. But you see, suppose I am inserting some information, suppose here, suppose in this byte. So I am inserting 1, 1, and 1, all 3 bits. So what is the change? 1, 2, 4. So total change is plus 7. Okay. Now, if it was 1, then if I could go for 0, then it will be minus 8. The change will be only minus 1. So that is called the handle or the adjustment. So I cannot perturb the inserted bit and bit position, but all other bit positions or bits are with me to adjust. That's why towards the end of my lecture, I will near equal to the maybe some chance. So to impart more security, I am adding another layer here. What is the layer? The layer is that I am not embedding into the pixel domain or the spatial domain. That means I am not perturbing the pixel values directly. Rather, I am using some transform equations. I am using some transform equations to transform my image from spatial domain to the spectral domain. And I am generating the frequency component. And I am embedding into this frequency component. And then I am converting the embedded frequency component into the spatial domain using some inverse transform. We know that the transform equations are reversible. So that I will show very quickly how much I can do within 1 hour or so. It may extend some more so that I can complete the task, whatever you given to me. And you can understand in a better way, and you can go ahead with some of these things if you can like it. So it's very interesting field. So I can use discrete Fourier transform, discrete cosine transform, wavelet transform, Z transform, and other transform, whatever I have given in my lecture. I'm coming to that. Still I didn't come because perspective is very important, the background and the study. So now I am telling you, if you go to the Z transform, So it's always generate the complex conjugate a plus ib, a minus ib. So there also we can embed. We have some papers on that. What normally we do that if we embed some redundant bit, we have to embed in both conjugate complex, then it will be all right. So now if we go to the frequency domain, normally what we have used here, normally we have used the image size 512 cross 512 pixels and authenticating image mostly 128 cross 128, and we are normally embedding into the real component, because when we are transforming the image from the spatial domain to the spectral domain, that means all the frequency components that we are considering that we are embedding into the real components only. We are not considering here into the imaginary component, at least for this talk. You see, these are some of the examples of that. So let us consider the basic DFT and IDFT, how we compute the transform coefficient. Because you see, here we have to go cleverly. I cannot convert my complete image in a single shot to the frequency component. That will surely generate the imaginary component into a maximum extent, and it is very difficult to handle the image and handle the secret bit. That's why the computation of this transform computation at the beginning, how you are going for it, what is the solution? The solution is that I am not going to transform the complete image in a single shot, rather I am taking a mask, maybe 1 cross 2, maybe 2 cross 2, maybe 3 cross 3, depending on your convenience how you can handle that. But if you go for suppose dihedral group 4, you will see that I can go for more in my mask size. So recently I have published one book. At the end I will show you the book by the Springer. So there all of these aspects we have covered, and complete workbook is there. That means all methodology.
Sir, here which variable you use for the frequency component, sir? Either u or v, or what are the u and v depicting, sir, in this slide, sir?
This is the transform equation. Okay, and from here we are using a mask. We are using a mask of 2 cross 2. You see, we are using a 2. This is the equation, and we are using a mask of 2 cross 2. How we are using? You see, let us consider the one-dimensional Fourier transform. So this is the equation for one-dimensional Fourier transform, and this is the inverse transform. So let us consider the computations that it is reversible. You see, I am using 10 and 20. So if we put 10 and 20, f0 is 10, f1 is 20. So f0 when I am computing, I am putting this. You see, n is 2, 1 by 2 into fx e to the power 0, it is 0. So now 0th position. So you are computing f0. You see, this is ultimately f0 equal to 15. Then f1, if I compute it, half into x equal to 0 to 1, fx e to the power twice pi jx2. But here we have a imaginary e to the power minus j pi equal to 1. The second component, what I will do, I will fabricate this e to the power minus j pi equal to cos pi minus j sin pi. So it will be minus 1. So now the f1 is minus 5. So this is your pixel and this is your frequency component. Now if we go to the reverse, using the inverse discrete Fourier transform, you see my coefficients are 15 and minus 5. So I am using the inverse transform equation. I am putting the values. You see, f0 e to the power 0, f1 e to the power 0 for f0. So you just add it up, then I am getting the first component, pixel component. For the second one, f1, you see, f0 e to the power 0 plus f1 e to the power j pi. Again, if you compute it, trivial computations. You see, e to the power j pi equal to minus 1. I am putting this j pi value. You see, I am getting. You see, this is a completely reversible. So that means the transformation is not any problem. So now embedding. What I am doing, suppose this is the frequency component I have generated after the transformation. These are all, and I am embedding this. Okay, so this LSB embedding, if I say that, here you see, if I embed 1, So it will be minus 1 instead of -2. So I have embedded it. And then after embedding, I shall go for inverse transformation. Now, surely we will ask the question that, sir, the pixel value will be different. So definitely the pixel value may be different. Now here you see I have made some clever thing. What is that? I have embedded into this 3 component coefficient, not I have used this DC component. That means that is available for adjustment. This is one of my way here. Not all cases, but most of the cases when some deviation is occurred. So you come to the pixel domain for this mask. After embedding, you see the deviations. What are the deviations? I am coming to that. The deviations may be, you see that when I am embedding, I am transforming, my pixel values are 0 to 255. But may I ensure that after computation of the transformation, the coefficient values will be within 0 to 255? How do we ensure that? That has to be ensured. So that's why you used to go for stretching. Suppose some coefficient, some pixel values are 0 to 12 or 0 to 15. So if it is 0, then I should take it up to 15. Then if it is 255, 4, so I had come down to 252. So degradation of image will not be there. So this will be the stretching of the image. That pre-processing, some of the pre-processing you have to ensure in your mind, and lot of various pre-processings are there. I am giving you this one pre-processing and one adjustment procedures. So this is the embedding. So you see this is the example that this is your pixel component of the image. I have taken 2 cross 2 block. I have converted using DFT. These are all frequency components. Then I have embedded and then I have transformed it. Then you see from the transform image, I have at the destination end, what the receiver will do. The receiver will go for only the forward transformation, not the inverse transformation. So if we go to the forward transformation, I shall get the frequency component, and from that frequency component, I have the embedded secrets. I shall extract the embedded secrets based on my hash functions or whatever be the logic I have used for embedding. Is maybe LSB embedding, is maybe using the hash functions, or it may be with the difference of the age, whatever may be. That is my logic. So I will extract the information accordingly. So you see that transform computations, reversible computations, I am just showing you. Sorry. So this is, you see, suppose I have 4 components A, B, and C, D. Let us compute very quickly. So it has M equal to 2, N equal to 2, equal to 0, and B equal to 0. So I am putting F 0, 0, and I am putting A, B, C, D instead of the numerical values. You see what will happen if we just compute trivial computations? Value will come as half of A plus B plus C plus D. So you see a complex transforming equation is reduced to a simple addition subtraction equation. That is why we have to use some.
Sir, I have a little doubt. Like for each image, we use the 2-dimensional DFT, or like, is it much more multi-dimensions we can add into that?
No, that is your algorithm. Suppose I am using half of the image 2 cross 2, half of the image 1 cross 2. No problem. That is your decision. You can take that decision. Okay. So you see, if we go for the 2 cross 2 mask, so this will be the equation, fabricating the equation here. So transform computation has to be done at the beginning. Otherwise, you cannot go for your embedding. So that is very important. So you see, and reverse transformation, you see, let's see, W, X, Y, Z, and this is your inverse transform equation. I put that, you see, I am getting this half of W plus X plus Y plus Z. You put the value of X, Y, Z, you see, is get the value F inverse equal to. So you see, this is again always reversible, but you have to keep it reversible. So the concern is that the converted value may be negative. The converted value may be a fractional number. The converted value may be greater than maximum. So for that, you have to go for pre-adjustment or readjustment. pre-embedding adjustment, post-embedding adjustment. So these are some of the outputs. Yeah, this is the embedded. So I have already discussed this, that you see that these are the places where I am embedding, but these are the places where I can play for adjustment. They are also same. These are the places I have embedded, but I can embed here also. No, not necessarily that's only LSB I will be an embedding. So anywhere I can embed based on my hash function. So now based on this, I am giving you the study of discrete Hartley transform, how I have computed the transform equations 1 cross 2 and 2 cross 2 mostly, and how I have embedded and what is the effect of that embedding, how can I enhance. Very quickly I shall go these results for discrete Hartley transform, binomial transform, Legendre transform, Stirling transform, group linear transform or dihedral group 4. So if you see my book, everything is given and it is extremely elaborated, and then embedded in the watermark size, quality of the enhancement and the inverse transform. So in this particularly we have embedded up to 3 bit per byte. That means I am perturbing 3 bit out of 8 bit in the pixel. That means my payload, it is called the payload. The payload is 3 BPB. Now there may be payload fractional 1.2. What is the reason? The reason is that I am not embedding uniformly in all pixels. I am selecting some pixel in using some algorithm and I am embedding there itself. So these are my objectives already have discussed, and we have embedded in the real components what we are discussing here, and we have used 2 cross 2 and 1 cross 2 masks. So now these 5 techniques, let's see, and quality enhancement of the technique. The first is discrete Hartley. So let us consider that this is the equation for discrete Hartley, and if you go for 2 cross 2 and 1 cross 2, this is 2 cross 2 transform computations, and this is the result. I'm not going into details, it is not possible. You can see it here, you can see from my book. And if you go for inverse transform, this is the inverse transform computation. This is the reduced equation from this equation. And if we call 1 cross 2 mask, this is the forward computation. This is the inverse computation. And these are some of the pixel adjustment methodology we have used here. I'm not going to discuss in details. So why you have used, you see that 2 to the power 8 means that whatever I have embedded, only after that bit towards the MSB, I have gone for adjustment. So my payload is 0.5 to 3 variable payload. Let's see the experimental results here. You see that we have 2 cross 2 masks, all 2 cross 2 masks, and I have embedded starting with 0.5, 1, 1.5, 2, 2.5 up to 3. This is your 3. And the PSNR is degrading gradually. And you see for 2.5, it is here, but for 3 it is here. It is sometimes it is coming below 30 PSNR. We know that for the acceptable limit of the image quality, our need is to keep the PSNR near equal to 30 or above 30. So somewhere we are embedding, we are violating the norm. So what we will do, we shall go for enhancement methodology to make up it. Towards the end, I'll show the same results is improving. You see, this is 1 cross 2 mask. Here also the same thing. Here also the same thing we have. You see 0.5, 1, 1.5, 2, 2.5, 3, and these are some existing. You have compared. They are only 1 and 2.5. No variable payloads and no variable images they have embedded. So now if we go for the average values of the PSNR, you see that when I am embedding 0.5 near about more than 45, then 1 it is coming down. You see around 20.
Sir, what does your PSNR depicting, sir, in short, sir?
Signal to noise ratio. Peak signal to noise ratio, it is the signal to noise ratio. Okay.
Okay, sir.
these are the metrics we use for the quality, to measuring the quality of the image, because not only embedding is your most important thing. The second important thing is that your image should not be degraded. If image is degraded, then you see no point of going for steganographic application. You remember, steganographic application will be failed. So here you see for 1x2 result, also you see for 2.5 is up to 30 is there, but when I am going for payload 3, it is degrading. So it is, you see, image fidelity, you see structural similarity index, and inverse index of image quality. So this should be ideally 1, this should be ideally 1, this should be ideally 1. Image fidelity is ideally 1, means the same image. Suppose I am taking two images, one is the embedded image and one is the original image. Suppose I did not embed any bit, so your IF will come as 1, SSIM will come as 1, UIQ will come as 1. So that means my motive is how much I can keep nearer towards 1. All of these matrices, my embedded algorithm will be better if it moves towards the value 1. You see, this is the deviations we have computed in terms of these two window, that 1x2 and 2x2. You see, deviation generally goes more for 2.5 and 3. You see, this is your standard deviation for your 0.5, 1, 1.5. These are payload 2, 2.5 and 3, and these are for various images we have used. And you see that the deviation is more towards higher, definitely. But how do you minimize that? That means this can be improved if we go for some pre-processing and post-embedding adjustment. So now let us consider the Legendre transform. How we have computed 2x2 and 1x2, both we have computed. So this is the original Legendre transform equation, and this is my transform computation using 2x2. It is the forward transform, and then this is the inverse transform. So definitely this is also reversible, what I have shown you during the DFT computations, I have shown you. And then these are some adjustments we have made, and formula we have made it. So you have to generate your formula, and embedding 0 to 3, 0.5 to 3 BPB we have embedded. And you see again here the carrier image and the peak signal to noise ratio. Peak signal to noise ratio here for 2x2 only. You see, for the 3, you see that Legendre transform for 3, it is degrading. But I will come later on show you it is 1x2. Here you see for the Legendre transform, it does not go below 30. That means if I use the Legendre transform and 1x2 mask, that means definitely the quality of the embedded image, the perceptive quality of the embedded image will be near, more near to the original image. That means the invisible communication is much more successful. Here you see that the average cases in both, for both, you see 0.5, 1, 1.5. So in terms of the payload, here payload is decreasing, but in case of, you see the average case for all these keys, this here it is again coming down. But you see SSIM, IF is 0.999, SSIM 0.998, UIQ 0.96. So all the matrices are confirming my situation that my embedding is good. And again, if we compare with the 2x2 window with 1x2 window for embedding, again you see 1x2 window give better result.
Sir, what is your SSIM depicting, sir? Case.
Structure similarity index. Similarity between the cover image, original cover image without embedding, and the cover image with embedded secret. There is a measure the difference between these two. What is the difference? If it is 1, that means both of the images are identical, same image. That means I have taken two images, same image, I have copied the image and I have computed the SSIM, I have computed the IF, I have computed the PSNR, whatever may QIF. So all are one. That means there is no difference, there is no perturbation, there is no noise injected into the image. That is the meaning. You see, these are the results for various embedding situations here. 0.5 BPB, 1 BPB, 1.5 BPB, then 2 BPB, 2.5 BPB. So let us consider the binomial transform. Very simple transformation, binomial equation. So transform equation. Here you see the computation is also very simple. Yeah, this is the two-dimensional forward, and this is the two-dimensional inverse transformation. And these are the embedding rules, and these are the results. Only in one images we are getting some bad results. Otherwise, you see, we are getting very good results for all cases, and the PSNR coming around 50. That is very good. And you see, for 1x2, here baboon image give some things, but still for 1x2 window gives much better result than you see your 2x2 window. Here is around 30 or coming down 30 some cases, but in this case for 1x2 window it's coming, you see, around 30 and 35 is the optimal, yeah, lowest results most of the cases except these two. That means we are preferring lower window for better result. That is another observation from my point of view. And you see, this is your graphical representation of variation of average PSNR. Whatever the average PSNR we have computed for various images, 5 images, we are make some average, and this is the values. You see, these are the 1x2 window, and these are again payload. These are the payloads. That means payload means bit per byte. How many bits we are perturbing out of 8 bits? That is the payload. And these are the metrics we are getting. Again, this is the deviations we are getting. Again, this is your experimental results for the payload in terms of the standard deviation. You see, for 2x2 window and 1x2 window, for 1x2 window deviation is less. Now we are coming to the Stirling transformation. Another transformation you see for Stirling transformation. These are the transform equations, and this is your forward computations for 2x2. This is your inverse computation for 2x2. Other I could not give, so slide will be much more. That's why. So these are some pixel adjustment for methodology we have used, and we have used some cat map for scrambling the secret information. These are the embedding rules. The embedding rules I can go for some hash functions or some philosophical functions that I am embedding first LSB plus 2, then 2 bits are embedded, LSB plus 2 minus 1, LSB plus 2 plus 1, whatever may be. That is the empirical methods I can use, or I can use some mathematical methods for embedding, or I can detect some edge area, I can detect some flat area. If it is a flat area, I shall embed 1 bit, and if it is an edge area, I shall embed 3 bit. That means some decisions you are taking, that will be between the understanding between the sender and the receiver. So these are the experimental results that we have the performance analysis for 2x2 windows. So you see, in some cases it's coming down for 2x2 window below 30. What is my major parameter? But in 1x2 window, it never cross down to 30. Again, I am telling that the smaller window always give better results. Here also, again the same thing it's showing. You see, and these are the parametric values for image fidelity, structure similarity index, universal quality index of the image. Again, this is the deviation. For that, you see, almost coherent. Whatever the results for all type of transformations, I am getting various. Then you see, nowadays we are using that symmetric operations of the group. So we are using the group theory, dihedral group of 4. That means it's a square. So in my book, you will see that we have used dihedral group of 20, and all reversible computations we have given extensively. You can go through that book if you have some interest on that. So we are using delayed D4, and this is your transform computations here, forward transform, and this is your inverse transform computation. Here you see in a dihedral group, here we have two components. One is the reflection coefficient, another one is your rotation coefficient, R and S. These two components together will reconstruct the image. Here image transformation is not simple transformation using the equation, is using the rotation and reflection, because it's the symmetric group. So we are considering the reflection and the rotation, we are combining these reflections and rotation together to generate the transform coefficient. And again, during the reverse or inverse computations, we are using the same concept to compute these things, and these are the equations. And this is your 1 cross 2 forward computations, these are, and this is 1 cross 2 reverse inverse computations. This is the embedding rule, and you see that what is the result? This fascinating result of this group transformation based embedding. You see, I have used same payload 0.5 to 3, but even in payload 3, for only one images, for the baboon images, normally baboon image is a typical image. So all other cases, our PSN are coming above 35. You see here, but even in case of baboon, it is above 30. So that means grouplet or Gillette transformation is very useful for this type of steganographic applications or the computation transform computations in terms of reversible and the steganographic applications. Here you see for 1 cross 2, here also the same thing, in both cases giving the optimal results. So this is the payloads, you see, and these are the various structure simulated index, image fidelity, SSIM, UIQ for both 2 cross 2 and 1 cross 2 mask. And these are the results, and this is the deviations. Here also you see deviation is very less. Here you see even 3 deviation is less. Now what I was talking about, that in some cases, particularly higher payload, the degradation of the image is such that the peak signal to noise ratio is coming down below 30. We should not accept that. So quality enhancement, two types of quality enhancement, you see, EMD, empirical mode decomposition, and GA we have used here. Particularly when I am going for higher payload greater than 2, you see that this is the original 2 cross 2. Then if we go for the enhancement, then you see, you see that it is improving a lot. Here is original. Then again, if we go for quality enhancement 1 cross 2, improvement is more, except this particular that means Legendre Transform. All other transforms are satisfying that your PSNR peak signal to noise ratio more than 30. This is again, this is your, you see, 2 cross 1 cross 2. This is 1 cross 2, all above 30 ensuring. Here you see, all of the cases we are enhancing the quality. Now we are using the genetic algorithm for enhancement also. How we are using the genetic algorithm? These are some of the parameters, but I am telling you that, you see, suppose I am telling you that first LSB3 I have embedded. So I cannot touch on these 3 LSB. I cannot touch on these 3 LSB. So rest 5 bits are available for me for adjustment. So these 5 bits we shall use for genetic algorithm to be applied here. And in this case, even we have applied multiple pixels for applying the genetic algorithm efficiently. So particularly for the mutation or crossover. That means first 5 bits of pixel 1 is swapped to the first 5 bit of pixel 2, something like that. Because, but what is my objective function? The objective function is that not to disturb the embedded image bit and to keep the deviation between the original pixel and the embedded pixel. It should be, deviation should be minimum. Most of the cases we used to keep the deviation within 10, limit of 10. So you see, this is the representation graph for that, for genetic algorithm based advancement 1x2. There you see, these are all the results, improvement of that results. I'm not going into details of that. These are there. So this, all these 4 methodologies we have used and compared for our work. This is one of our researchers, of our scholars, and you see the existing methodology, whatever we have got, they didn't go for any variable payload here, but our is variable payloads, and you see we have gone for up to 3 BPP, but they have gone for 0.25 and you see 0.34, something like that. And you see PSNR deviation prior to the GA is more, but when I am going for application of GA or quality enhancement, it is less. And even you see, when I'm talking, coming here, you see what you see, this only 1 cases or 2 cases less somewhere. Otherwise, you see we are satisfied. Even some cases it is crossing the 52, 53 limit here also. Yeah, these are the some of the results you can see that for the quality enhancement. So now, what are the target achieved? We are authenticating the color image, we are achieving the variable payload, we are going for good adjustment, good acceptable quality of the embedded image, and we are preventing the underflow, overflow, and we are embedding into the real coefficient, and we are going for quality enhancement through GA and other. These are some of the reference, these are some of the publications. This is the book. This is the book published, and this is the URL of the book. You can see that here we have 16 chapters. So all chapters, even here we have used the chaos theory. Also, you see that nowadays NIST is talking about the test bed conditions. 15 test bed parameters they are specified. So everything has been discussed and it has been applied in some neural network based systems, and it has shown how it is working there. Even chaos theory is also used for generating the good random numbers, and how chaos theory can be tested. That's are also given along with spatial domain, spectral domain. Mostly these are transform domain computations and the steganographic applications. So all 1-dimensional, 2-dimensional, 3-dimensional methodologies are given along with working example also. All examples are given for transform computations, embedding, extraction, and then the experimental results after implementation. So this is from my side. Now I will love to go for questions.
So thank you very much, sir, for this wonderful talk. So we are receiving multiple questions from the audience, from both
Definitely.
the chat. So as because we are running out of time, so we will take a few of them, and rest of them will forward to our sir. And
Definitely, my mail is with you. You can give the mail. My website is there, jkmandal.com. They can go to the website. A lot of materials are also there. Maybe this material is also uploaded there. So I
sure.
So you can go it. I love to interact with all of you. We
So
are
a few of the questions I'm taking from the chat, sir. So one question is like, can a private key be used in an asymmetric environment? encryption method to encrypt information with a known output to establish that a message originated from a reliable entity? Or does this expose how to decode all the information encrypted with the public key?
Actually, today we have discussed on steganography, invisible communication. So we did not consider the cryptography. The cryptography is called the scrambling the source image, and everyone will see that it has been scrambled. But my intention was not to scramble the image, not to degrade the image. But if we use some secret key or private key or pair of key, we normally use, no harm. We can use same key exchange methodology. Everything can be applicable here. So
Okay.
that is your
So,
methodology, you can associate, no problem.
sure. Thank you for answering this. Moving to the next one is that I have heard that the majority of reversible data counseling strategies have a limited embedding capacity. So, is there any method or algorithm by which we can increase the embedding capacity while keeping the same security protocol for reversible image construction for cryptographic data?
Thank you for the question. Devorsi, I think during my presentation, you have seen that for my cases, this work is done, I think, 3-4 years back.
Yes.
It is up to 3 BPB. I have already part up 3 bit in your transform coefficient out of 8 bit. So my standard payload is 3. Nowadays it is going towards 3, 3.5, towards 4 as this adjustment methodology is improving. I am using deep learning methodology, I am using neural computing techniques, lot of techniques we are using. So methodology, how I can use, what will be the mask size, what will be the embedding algorithm, what will be the adjustment algorithm. Your capacity will depend on that only. And only the thing you have to see is that nowadays the NIST test bed condition, they have given 15 test bed condition. How much of them you passed by your algorithm? And what is the payload you have achieved? That is your algorithm. And you read the literature of this latest publications, I think you will get a lot of algorithm like this and lot of various methodology for upgrading the payload. That is possible.
Sir, which parameter we are exploiting here in terms of payload, sir?
Parameter means we are, when I am increasing the payload, the first and foremost parameter you have to see is that the peak signal to noise ratio. We know that I am doing the thing on the image, so I cannot expect that my quality of the image will be degrading much. So what is the limit? The limit is that PSNR cannot decrease below 30. So it should be near absolutely above 30. So we used to keep around 35, 36 to 40. Then only we accept that my method is good. This is the first thing.
Sir, what
Then
is, yes, sir, what is we are saying here payload, sir? Is it the image we are saying it is payloaded? What is payload exactly?
payload
Because
means that
because in ISRO we because in ISRO we take like different things, na sir? Payload.
payload
What is
means
here
the
payload,
definition
sir?
of payload is out of 8 bit in a pixel, how many bit you are perturbing. This is the payload. Okay, suppose 1
Okay.
pixel I did not perturb. So payload
How
for
many bits
that
to go?
pixel. No, that thing is that payload will be computed
Okay.
for entire image, not for the mask. Payload will be computed for entire image. Suppose
Okay.
in a mask I did not embed. In another mask I have embedded maximum. So it will be average. Suppose total 264 bit was the byte was the image size. Now I have embedded 30 bit. So you see, you convert it byte and you just calculate the payload accordingly. It is a very trivial thing. That means, and normally we see that for a complete image, what was the size of the image and what is the size of your secret message. This ratio is the payload. And it is normally
Got it, sir.
called bit
Got
per
it.
byte. I think got my point, no?
Yes, sir. Yes.
Okay, so participants, we are almost running out of time. So I know that the close questions are continuously flowing in. So what we can do is that we can share the website of sir and also the study materials along with contact details with all of you, so that you
Yeah,
can
yeah,
contact sir and get your questions.
yeah,
So
definitely.
right now, I would like to just share one token of appreciation. So, sir, can you kindly stop
Yeah, yeah.
sharing?
Just 1 minute. Yeah, I stop my sharing.
Okay, so I think my screen is visible. So this is a small token of appreciation on behalf of IEEE Student Branch IIT Kharagpur to our beloved Jyotsna Mandal, sir. So this is a
Thank
virtual
you.
memento for appreciating our invitation and also coming virtually, but we expect sir to come sometimes in our campus and give us a talk physically in near future. So
Definitely, I
in
will have to come there. So sometimes,
uh, it's always great to hear, sir, from like he's a very busy and he's giving talks in other student branches and various conferences. We all know him for that.
yeah, yeah,
But probably soon in near future we'll have both Jyotsna sir and Devashish sir together sometimes in our campus.
yeah.
So that
Love
will
to
be a
hear
great.
the feedbacks from all of you, and so love to be associated with you. Don't worry. Anytime they can mail me. So no problem. I will be always with you. Any help, and I love that someone of you inclined to this field to work somewhat. That will be my mission and vision
Yes,
for
sir.
you,
Yes, sir.
so that my
Yes.
lecture will be successful. Okay,
Sure,
I'll
sure.
share
Most of
this
the
PPT to
many of
you.
the students working in this field in our campus as well, and probably they
Yeah.
will get many information, and probably they may contact you as well,
Yeah, yeah,
because
definitely. So I'll share the PPT to you. Don't worry.
sure, sir. Sure. So we'll
Yeah,
forward them to our participants as well.
yeah, yeah, yeah. Okay.
So
Thank you very much.
so before we end, I'd like to request all the participants to kindly turn on their camera. Those whoever would like to be in the frame with sir, and we'll take a snap the entire thing. So kindly turn on your cameras, and I would like to request Akashji to kindly take a snap with our guest speaker today.
Yes. Yes, Devoshi. All of you, please turn on your cameras.
No, those would like to capture this moment because it's a
Yeah.
rare thing that we have sir amongst us.
Oh,
Please turn on your camera, those who'd like to capture this moment so that we can have a quick snap. Yagas, if you can please go ahead and let us know once take the snap.